You flip a coin. Before it lands, you say there is a 50% chance of heads. That statement feels clean and precise. It has a number attached to it. It makes a prediction. And when the coin lands, you can check whether the prediction was useful. Probability in that moment feels like one of the most straightforward tools available for describing uncertainty. You do not know what will happen. You assign a likelihood, and reality eventually delivers one answer. That picture is so familiar, it feels like it requires no examination, but it is resting on an assumption so basic that it almost never gets named. The assumption is this: only one outcome actually occurs. The coin lands heads or it lands tails. One of the two possibilities becomes real and the other one does not. Probability is the tool for navigating that selection process before it happens. It is a measure of how likely each possible outcome is to be the one that gets chosen by reality. Every use of probability in everyday life inherits this assumption silently. Weather forecasts assign likelihood to futures, exactly one of which will arrive. Medical statistics describe the proportion of patients who recover, meaning the rest do not. Risk assessments weigh scenarios against each other on the understanding that the world will follow one path and leave the others untraveled. The entire architecture of probability as a practical and mathematical tool is built on the foundation that possibilities compete and only one wins. This is not a naive assumption. It is consistent with everything observable at human scales. Coins do land on one side. Patients do either recover or they do not. The world does appear to select one outcome and discard the rest, and it does so with a consistency so complete that questioning it feels unnecessary. Quantum mechanics makes it necessary. At the scale where the laws governing all matter actually operate, the claim that only one outcome occurs turns out to be extraordinarily difficult to defend. The mathematics that describes quantum events does not select one outcome and discard the rest. It carries all outcomes forward simultaneously, weighted by numbers whose physical meaning becomes deeply unclear the moment you ask what they are actually describing if everything is happening at once. What does it mean to say something has a 50% probability of occurring if it always occurs? What is the number measuring if there is no selection, no discarding, no single outcome that reality lands on? That question is not a philosophical curiosity sitting at the edge of physics. It is a structural problem living at the center of the most precisely tested scientific theory ever developed. And the answer requires dismantling and rebuilding the concept of probability from the ground up. If you like exploring questions like these, feel free to leave a like and subscribe. Tell me where you are watching from, and if there is something about the universe you find yourself wondering about, let me know in the comments. With that said, let's get back to the topic. The first thing to dismantle is the assumption that quantum mechanics actually does select one outcome, because the case that it does not is considerably stronger than it might initially appear. Take a single electron and fire it at a barrier with two narrow slits cut into it. Behind the barrier, place a screen that records where the electron lands. Before it reaches the barrier, the electron is described by a wave function, a mathematical object that spreads through space and carries information about where the electron might be found. That wave function passes through both slits simultaneously, not metaphorically, not as a shorthand for uncertainty about which slit it used. The wave function physically propagates through both openings, and the two portions interfere with each other on the far side the way two overlapping water waves interfere, reinforcing in some places and cancelling in others. The interference pattern that builds up on the screen over many electrons is the direct physical signature of this. The pattern has peaks where the two wave function portions reinforced each other and gaps where they cancelled. That pattern cannot be produced by electrons going through one slit or the other. It requires both portions of the wave function to have been physically real and interacting. The experiment is not consistent with the electron having a definite position that was simply unknown before measurement. It is consistent only with the electron genuinely occupying a superposition, a state in which multiple possibilities are simultaneously physically present and causally active. This is not specific to electrons or to the double-slit setup. It is the general structure of quantum mechanics as a description of physical reality. Any quantum system that has not been measured exists in a superposition of its possible states, with each possibility carrying a complex number called an amplitude. The amplitude is not a probability. It is something more fundamental from which probabilities are extracted by a specific rule, but the amplitudes themselves describe the simultaneous physical presence of multiple possibilities in the evolution of the system. The wave function governing that system evolves according to the Schrödinger equation, and that equation is linear and deterministic. Given an initial wave function, the equation produces exactly one future wave function, with complete predictability. There is no randomness in the evolution. There is no selection of one possibility over others. The equation carries all possibilities forward, weighted by their amplitudes, and it does so without discarding anything. This creates an immediate tension. The Schrödinger equation says, everything evolves deterministically with all possibilities intact. But when a measurement is performed, only one outcome is observed. The screen records the electron at one specific location, not smeared across all the locations the wave function assigned amplitude to. Something appears to have selected one outcome and collapsed the rest. The question of what that something is, and whether it is real or apparent, is where the deepest problem in quantum mechanics lives. The tension identified at the end of the last segment has a name. It is called the measurement problem, and it is not a gap in experimental knowledge that better instruments will eventually close. It is a logical conflict sitting inside the mathematical structure of quantum mechanics itself, between two descriptions of how physical systems change over time that cannot both be universally true. The first description is the Schrödinger equation. It governs the evolution of any quantum system, and it is continuous, deterministic, and linear. It carries superpositions forward intact. It does not select outcomes. It does not collapse anything. Applied to an electron in a superposition of two positions, it produces a future state that is still a superposition of two positions, with the amplitudes shifted according to the dynamics of the system. Nothing is lost and nothing is chosen. The second description is what appears to happen during measurement. When a detector interacts with that electron, the superposition seems to collapse. The detector registers one outcome. The other possibilities, which the Schrödinger equation was carrying forward with non-zero amplitude, appear to vanish. The system goes from a spread of simultaneous possibilities to a single definite result, and it does so instantaneously and irreversibly in a way the Schrödinger equation does not describe and cannot produce. The conflict is direct. If the Schrödinger equation governs all physical processes, it must also govern the interaction between the electron and the detector, since the detector is itself a physical system made of particles subject to quantum mechanics. Applying the equation to that interaction does not produce a collapsed state with one outcome. It produces a larger superposition in which the detector is now entangled with the electron, carrying forward all the possibilities the electron was carrying, now encoded in the combined state of the electron and detector together. The measurement has not collapsed anything. It has expanded the superposition to include the measuring device. Extend this further. The detector is read by an experimentalist. That experimentalist is also a physical system. Applying the Schrödinger equation to the interaction between experimentalist and detector produces a larger superposition still, one in which the experimentalist is entangled with the detector and the electron, with all outcomes still present in the combined wave function. There is no point in this chain where the equation naturally produces a single outcome. The superposition simply grows, absorbing each new system that interacts with it, expanding without collapsing, and yet the experimentalist observes one outcome, not a superposition of outcomes, not an ambiguous blur of possibilities, one definite result with the others absent. Something is happening that the Schrödinger equation does not account for, and identifying what that something is has divided physicists into competing interpretations for nearly a century. The answer to that division is what sets up everything that follows in this chain. The most direct response to the measurement problem is also the most radical. It takes the Schrödinger equation seriously as a complete and universal description of physical reality, applies it without exception to every system including detectors and observers, and asks what that implies without adding anything external to make the math produce a single outcome. The answer it arrives at is that the single outcome is an illusion of perspective. All outcomes occur. The equation was right all along. This is the many worlds interpretation, proposed in its original form by Hugh Everett in 1957, and it resolves the measurement problem not by explaining the collapse but by eliminating it as a physical event. There is no collapse. The wave function never collapses. It continues evolving according to the Schrödinger equation through every interaction, including measurements, and every possibility it carries forward becomes physically real in a distinct branch of the total quantum state. When the electron reaches the detector does not register one outcome while the others disappear. The detector registers all outcomes, each in a different branch of the wave function. When the experimentalist reads the detector does not observe one result while the others vanish. The experimentalist becomes entangled with the detector and branches along with it, with each branch containing a version of the experimentalist who observed a specific definite result. From inside any one branch, the experiences of a single outcome having occurred. From the perspective of the total wave function, all outcomes occurred simultaneously, and all persist. The interpretation requires no additional mechanism beyond the Schrödinger equation itself. No collapse postulate, no special role for observers, no division between quantum and classical regimes. The equation is applied universally and taken at face value. What it produces is a structure in which reality is vastly larger than any single observer's experience of it, and in which every quantum possibility is not a road not taken, but a road that is taken by a version of the observer that is just as real as any other. This is where the problem of probability becomes acute, because if every outcome occurs and every branch is real, the statement that an outcome had a certain probability of occurring loses its ordinary meaning entirely. Probability was a measure of likelihood before selection. If there is no selection, if all possibilities are realized, what is the probability measuring? That question requires understanding what a branch actually is before it can be answered. The word branch is easy to misread. It suggests something like a tree diagram, a clean fork in a path where two roots diverge and separate cleanly into distinct futures. That image carries spatial intuition that does not accurately reflect what is happening in the quantum mechanical description. A branch is not a parallel universe sitting somewhere else in space. It is a distinct component of the total wave function of the universe, and understanding what that means physically requires sitting with the mathematics long enough to let it replace the spatial picture. The wave function of any quantum system lives not in ordinary three-dimensional space, but in a much larger mathematical space called configuration space, whose dimensions scale with the number of particles in the system. For a system containing two particles, the wave function is a function defined over the space of all possible configurations of those two particles simultaneously. For a system containing every particle in the observable universe, the wave function is a function defined over an almost incomprehensibly large configuration space. It is a single mathematical object, but it is defined over a space so large that distinct regions of it can evolve in complete independence from each other once they have separated sufficiently. When a quantum measurement occurs, the wave function of the combined system, particle plus detector plus observer, develops structure in this configuration space that separates into components with negligible overlap. Each component corresponds to one outcome of the measurement, with the detector registering that outcome and the observer perceiving it. The components do not interact with each other because interaction in quantum mechanics requires overlap in configuration space, and once the components have separated far enough, that overlap becomes so small it is for all practical purposes zero. The branches become causally isolated from each other, not because they are in different locations in space, but because they occupy non-overlapping regions of configuration space. This causal isolation is what makes each branch physically real in a meaningful sense. A branch is not a hypothetical or a possibility. It is a region of the actual wave function of the universe, carrying forward a complete and consistent physical history, with matter, energy, observers, and causal relationships all intact and evolving. The observer in each branch has access only to that branch, not because the others are hidden behind some barrier, but because interaction between branches requires overlap that no longer exists. Each branch is as real as any other, and none has privileged status in the mathematics. This is the point where the probability problem sharpens into something genuinely difficult. If every branch is equally real, and every outcome is instantiated in some branch, then asking which outcome is more probable seems to be asking which branch is more real than the others. But the mathematics assigns them equal physical status. What then is the probability actually tracking? And why does the number assigned to an outcome before a measurement bear any relationship to anything that happens after it, given that everything happens? If every branch is physically real and every outcome occurs, then the ordinary concept of probability appears to have lost its object. Probability was always a statement about which possibility would be selected by reality. Remove the selection, and the statement seems to refer to nothing. This is not a minor technical difficulty requiring a small adjustment to the framework. It is a foundational problem, because probability is not peripheral to quantum mechanics. It is central to it. Every experimental prediction quantum mechanics makes is a probabilistic prediction, and those predictions match observation with extraordinary precision. Whatever probability means in a many-worlds framework, it has to recover that predictive precision, or the interpretation fails on its own terms. The most immediate attempt to resolve this is to reframe probability as a statement about proportion rather than selection. If every outcome occurs, perhaps the probability of an outcome is simply the fraction of branches in which that outcome appears. A coin flip produces two branches, one with heads and one with tails, and each has a probability of 1/2, because each accounts for half the total branches produced. That reframing feels natural and preserves the intuitive connection between probability and counting. It fails almost immediately. Consider a quantum event with two possible outcomes where the amplitudes assigned to each outcome by the wave function are not equal. One outcome carries an amplitude whose square is 3/4, and the other carries an amplitude whose square is 1/4. Quantum mechanics predicts that the first outcome will occur with probability 3/4 and the second with probability 1/4. But the branching structure produces exactly two branches, one for each outcome. If probability is branch proportion, each outcome gets probability 1/2 regardless of the amplitudes. The branch counting approach cannot reproduce the predictions of quantum mechanics, and therefore cannot serve as the foundation for probability in this framework. This failure is significant because it closes off the most intuitive escape route. The probability assigned to an outcome in quantum mechanics is not determined by how many branches contain that outcome. It is determined by the amplitude the wave function assigns to that outcome, specifically by the square of that amplitude. That rule is called the Born rule, and it is the bridge between the mathematics of quantum mechanics and the probabilities that experiments actually measure. In a universe where all outcomes occur, the Born rule is not explaining which outcome gets selected. It is doing something else entirely, and identifying what that something else is requires a completely different approach to what probability is even meant to describe. The branch counting failure points towards something important. Probability in a many-worlds framework cannot be about the structure of what happens at the level of outcomes, because at that level everything happens equally. It has to be about something else, something that varies between branches even when all branches are equally real. The only candidate the mathematics offers is the amplitude itself, and specifically its squared magnitude. The question is what physical meaning that quantity carries when selection has been removed from the picture entirely. The squared amplitude is a number attached to each branch of the wave function. It is always positive, it sums to 1 across all branches of any given quantum event, and it matches the observed frequencies of outcomes in every experiment ever performed with sufficient precision to test it. Whatever it is clearly tracking something real. The difficulty is identifying what that something is in a framework where every branch occurs and none is preferred over any other by the physics of the situation. In the standard non-many worlds treatment of quantum mechanics, the squared amplitude is simply defined as the probability of that outcome occurring. The Born rule is a postulate, an assumption added to the theory alongside the Schrödinger equation, not derived from it. It works with extraordinary accuracy, so the postulate is accepted, and the question of why it should be a probability in the first place is set aside as either unanswerable or unnecessary. The theory makes predictions, the predictions match reality, and the foundations are left to philosophers. In a many-worlds framework, that move is not available. If the interpretation is committed to taking the Schrödinger equation as the complete description of reality, then every other feature of the theory, including probability, must be derived from that equation rather than added alongside it as an independent postulate. The Born rule cannot simply be assumed. It has to emerge from the structure of the wave function itself, and it has to emerge in a way that explains not just what the squared amplitude is mathematically, but what it means physically for an observer, who will inevitably end up in one branch and experience one outcome. This is where the problem reaches its deepest point. The challenge is not mathematical. The squared amplitudes are there in the wave function, they sum correctly, they reproduce experimental predictions. The challenge is interpretive. What is an observer, about to undergo a branching event, actually uncertain about if all outcomes are going to occur? What is the probability a statement about, if not which outcome will be selected? One response is that the observer is uncertain about which branch they will find themselves in after the branching occurs. But this response has a hidden assumption embedded in it, namely that there is a fact of the matter about which branch a given observer ends up in. That observer identity threads through the branching event and lands on one side. That assumption turns out to be far more complicated than it appears, and examining it carefully is what opens the path toward a coherent account of probability in a universe where everything happens. Before that examination can happen, the mathematical tool that gives probability its quantitative content in this framework needs to be precisely identified. The failure of branch counting as a foundation for probability runs deeper than the specific numerical mismatch identified earlier. It reveals something structural about what probability cannot be in a many-worlds framework, and following that structural failure to its conclusion is what points toward what probability must be instead. Branch counting fails because it treats all branches as equivalent units. It assumes that the relevant quantity for assigning probability is the number of branches containing a given outcome divided by the total number of branches produced. But the wave function does not treat branches as equivalent units. It assigns each branch an amplitude, and those amplitudes carry physical information that branch counting discards entirely. Any account of probability that ignores amplitudes is an account that throws away the most physically meaningful quantity the wave function contains, and it predictably fails to reproduce the predictions that those amplitudes generate. But the failure goes further. Branch counting is not just numerically wrong, it is conceptually unstable. The number of branches produced by a quantum event is not a fixed or well-defined quantity in general. It depends on how the event is described, at what level of detail the branching structure is analyzed, and what counts as a distinct outcome. A quantum event can be decomposed into sub-events, each producing its own branching structure, and the total branch count depends on the decomposition chosen. There is no decomposition-independent fact about how many branches a given event produces. A probability measure built on branch counting therefore varies with the description rather than with the physics, which means it is not tracking anything real in the wave function at all. This instability points directly at what a valid probability measure in this framework must satisfy. It must be defined in terms of quantities that are intrinsic to the wave function and independent of how the branching structure is described. The squared amplitude satisfies this requirement. It is determined by the wave function itself. It does not depend on how outcomes are grouped or decomposed, and it is preserved under the linear evolution of the Schrödinger equation in a way that makes it a natural, conserved quantity of the branching process. It is the only quantity the wave function provides that has these properties simultaneously. So the squared amplitude is the right quantity. The remaining problem is justifying why it should function as a probability in the experiential sense, meaning why an observer facing a branching event should treat it as a measure of how confidently to expect one outcome over another, given that both outcomes will occur and both versions of the observer will exist after the branch. That justification cannot come from the structure of outcomes, since all outcomes are equivalent at that level. It has to come from somewhere else entirely, and the place it comes from is a framework for decision-making under a very specific and unfamiliar kind of uncertainty. The Born rule states that the probability of observing a particular outcome of a quantum measurement is equal to the squared magnitude of the amplitude the wave function assigns to that outcome. It is a precise and simple statement, and its experimental track record is perfect. Every quantum mechanical prediction that has ever been tested has been tested using this rule, and every test has confirmed it within measurement precision. It is not an approximation or a limiting case. It is the exact bridge between the mathematical structure of quantum mechanics and the numbers that appear in laboratory results. In the standard formulation of quantum mechanics, the Born rule is simply postulated. It is written into the theory as a foundational assumption alongside the Schrödinger equation, accepted because it works rather than because it has been derived from something deeper. This approach is pragmatically successful, but theoretically unsatisfying, because it means quantum mechanics contains two separate descriptions of how systems evolve: the deterministic continuous evolution of the Schrödinger equation and the probabilistic discontinuous collapse described by the Born rule, with no account of how or when the transition between them occurs. The measurement problem is in this gap. In a many worlds framework, the Born rule cannot be postulated as a description of collapse, because there is no collapse. It has to be derived as a statement about something else entirely. The question is what that something else is, and the answer begins with recognizing what the squared amplitude actually measures geometrically within the mathematical structure of the wave function. The wave function of a quantum system is a vector in a mathematical space called Hilbert space. When a measurement occurs and the wave function develops a branching structure, the branches correspond to components of that vector, pointing in different directions in Hilbert space. The squared amplitude of each branch is the squared length of the corresponding component. Squared lengths in Hilbert space are preserved under the evolution of the Schrödinger equation, which means the squared amplitudes of branches are stable quantities that do not change as the branches continue evolving after the split. They are geometric properties of the wave function that persist. This geometric stability is what makes squared amplitudes candidates for a conserved probability measure. A quantity that changes arbitrarily after a branching event cannot serve as a meaningful measure of anything consistent across time. Squared amplitudes do not change, which means whatever they are measuring something that remains true about each branch indefinitely after the split. The Born rule is not arbitrary from this perspective. It is the unique probability measure that is consistent with the geometric structure of Hilbert space and preserved under quantum evolution. Every other assignment of probabilities to branches either violates the geometry or changes under evolution in a way that makes it self-contradictory as a probability measure. This uniqueness result narrows the field considerably. The Born rule is not one option among many for assigning probabilities in a many-worlds framework. It is the only option that is mathematically coherent, given the structure of the theory. But uniqueness is not the same as justification. Showing that the Born rule is the only consistent probability measure still leaves open the question of why an observer should use it as a guide to expectation before a branching event, given that all branches will occur. That question requires stepping outside the mathematics and into the experience of the observer who is about to split. The approach that has made the most progress in justifying the Born rule from within the many worlds framework does not begin with physics. It begins with decision theory, the mathematical study of how rational agents should act under uncertainty. The move is deliberate. If the question of what probability means for an observer facing a branching event cannot be answered by looking at the branching structure itself, perhaps it can be answered by asking what a rational observer should do when facing that event, and then showing that the Born rule is the only consistent answer. The setup is precise. An observer is about to perform a quantum measurement with two possible outcomes. They know the wave function, they know the amplitudes, and they know that both outcomes will occur in distinct branches. They are offered a bet, receive a reward in the branch where outcome A occurs, and nothing in the branch where outcome B occurs. How should they value that bet? What is it worth to them before the measurement is performed? The question has content because the observer has preferences. They would rather be the version of themselves that receives the reward than the version that does not, even knowing both versions will exist. They are making a decision that will determine what one of their future branches experiences, and they want to make that decision well. Decision theory asks what constraints rationality places on how they should assign value to the bet, given everything they know about the branching structure and the amplitudes. The argument, developed most carefully by philosopher David Deutsch and later refined by physicist David Wallace, proceeds by identifying a set of constraints that any rational decision procedure must satisfy in this context. These constraints are not specific to quantum mechanics. They are general rationality requirements: consistency across equivalent situations, independence of irrelevant alternatives, and transitivity of preferences. Applied to the quantum branching context, with the additional physical input that branches related by certain symmetries of the wave function must be treated equivalently, these constraints uniquely determine how bets should be valued. The result is that a rational observer must value outcomes in proportion to their squared amplitudes. Any other valuation scheme violates at least one of the rationality constraints when applied consistently across all possible quantum bets and branching structures. The Born rule emerges not as an assumption about physical collapse or outcome selection, but as the unique rational response to the situation of an observer who knows they will branch and wants to make decisions that serve all their future selves as well as possible, given the geometric structure of the wave function. This derivation does not eliminate the strangeness of the situation. It does not make branching feel ordinary or resolve every philosophical tension in the interpretation. What it does is show that probability in a many-worlds framework is not a free parameter that can be set arbitrarily. It is constrained by rationality to match the Born rule exactly, which means the extraordinary predictive success of quantum mechanics is not a coincidence of the interpretation, but a necessary consequence of what it means to reason well in a branching universe. The decision theory argument establishes that a rational observer must weight outcomes by their squared amplitudes, but sitting behind that conclusion is something that deserves closer examination, because the nature of the weighting is unfamiliar in a way that the formal argument can obscure. When an observer assigns weight to a future branch, what are they actually doing? What is the weight attached to, if not the likelihood of that branch being the one that occurs? In ordinary decision theory, weighting a future outcome by its probability reflects a belief about how likely that outcome is to be the one reality selects. The weight is epistemic. It tracks ignorance about which possibility will be actualized. An observer who assigns probability 3/4 to outcome A is saying they believe reality is 3 times more likely to land on A than on B. The weight is a measure of credence about a future fact that is currently unknown but will become determined. In a many-worlds framework, that interpretation is unavailable. There is no future fact about which branch reality will select, because reality selects all of them. The weight cannot be tracking likelihood of selection. It has to be tracking something else, and identifying what that something else is requires thinking carefully about what the observer actually cares about when they make a decision before a branching event. What the observer cares about is the welfare of their future selves across all branches. Both versions of them will exist, both will have experiences, and both will bear the consequences of the decision made before the split. A decision that produces a good outcome in a high amplitude branch and a poor outcome in a low amplitude branch is not equivalent to a decision that produces those outcomes in reverse, even though both decisions result in one future self experiencing each outcome. The asymmetry comes from the squared amplitude, which represents the geometric weight of each branch in the total wave function, and which persists unchanged through all subsequent evolution. Weighting future branches by their squared amplitudes is therefore not a statement about which branch is more likely to occur. It is a statement about how much of the wave function structure is concentrated in each branch, and implicitly about how much of what the observer will become is carried in each direction after the split. A branch with a large squared amplitude carries more of the total quantum state forward. A branch with a small squared amplitude carries less. An observer who cares about their future selves in proportion to how much of their current quantum state those future selves inherit is rationally led to weight branches by their squared amplitudes, and that weighting is precisely the born rule. This reframes probability entirely. It is not a measure of ignorance about which future will occur. It is a measure of how the observer's current quantum state is distributed across the futures that will all occur. The probability of an outcome is the fraction of what you currently are that will become the version of you experiencing that outcome. That is a strange and unfamiliar thing to call a probability, but it is mathematically precise, physically grounded in the wave function, and fully consistent with every experimental result quantum mechanics has ever produced. The reframing introduced in the last segment rests on a claim that needs examination. It treats the observer's quantum state as something that divides across branches, with each branch inheriting a portion of it proportional to the squared amplitude. That picture implies something specific and uncomfortable about personal identity across a branching event, and following that implication honestly is what makes the reframing either coherent or empty. Before a branching event, there is one observer. After it, there are two, each in a distinct branch, each with a complete and continuous memory of being the observer before the split, each with equal claim to being the continuation of that observer. Neither is a copy in any meaningful sense. Neither is more original than the other. The branching does not duplicate the observer the way a photocopier duplicates a document, producing an original and a facsimile. It produces two continuations that are symmetric in every relevant respect, except the branch they inhabit and the outcome they observe. This creates a genuine puzzle about what personal identity means across a branching event. The pre-branch observer cannot coherently ask which branch they will end up in, because that question presupposes a fact that does not exist. There is no thread of identity that passes through the branching and lands on one side. Both continuations are equally them, and asking which one is really them is like asking which half of a divided river is really the original river. The question does not have an answer because the concept it relies on does not apply to the situation, and yet the pre-branch observer has to make decisions. They have to act before the split in ways that affect what their post-branch continuations experience. The absence of a fact about which branch they will inhabit does not release them from the practical necessity of choosing, and choosing well requires some framework for valuing the outcomes their different continuations will face. The decision theory argument establishes that this framework must be the born rule weighting. But what grounds that weighting, given that both continuations are equally them, is precisely the distribution of their current quantum state across the branches. What this implies about identity is that the observer, in some physically precise sense, is present in both branches after the split, but not equally. The branch with the larger squared amplitude carries more of the total quantum state that constituted the observer before the split. The branch with the smaller squared amplitude carries less. Identity in this framework is not a binary property that either does or does not persist through the branching. It is a graded property, distributed across branches in proportion to their squared amplitudes, and probability is the measure of that distribution. This is deeply counterintuitive because everyday identity feels binary and continuous. You are either the person who walked into the room or you are not. But in a branching universe, that intuition is a feature of living in a regime where quantum amplitudes are so sharply concentrated in single branches that the distribution across alternatives is effectively zero for all practical purposes. The graded nature of identity across branches is always there in the mathematics. It only becomes experientially relevant when the branching structure is made explicit, as it is in a quantum measurement, and when the question of what to expect from your future selves forces you to confront what those future selves are and how much of you they carry. Everything established so far has been building toward a redefinition. Probability in a many-worlds framework is not a measure of which outcome reality selects, because reality selects all outcomes. It is not a measure of how many branches contain a given outcome, because branch counting fails to reproduce the born rule. It is not an expression of ignorance about a future fact, because the future fact of which branch occurs is not a fact that exists. What probability measures in this framework is the fraction of the observer's current quantum state that will become the version of the observer experiencing a given outcome. That redefinition has a consequence that runs deeper than the mathematics. It means probability is fundamentally a statement about experience rather than occurrence. An outcome with a large squared amplitude is not more likely to occur than an outcome with a small squared amplitude. Both occur. What the large squared amplitude means is that more of what the observer currently is will become the experiencer of that outcome. The probability is a measure of the distribution of future experience across a branching structure, weighted by the geometry of the wave function. This shifts what a probability statement is doing when it is made before a measurement. Saying that outcome A has probability 3/4 is not a prediction about which branch reality will land on. It is a statement about how the observer's current quantum state is partitioned by the impending branching event. 3/4 of what they currently are will become the version that observes outcome A. 1/4 will become the version that observes outcome B. Both versions will exist, both will have complete and continuous experiences, and both will remember making the probability statement before the measurement. But the version observing A carries 3 times the quantum state weight of the version observing B, and that asymmetry is what the probability was always tracking. This reframing preserves everything that makes probability useful in practice. An observer who weights outcomes by their squared amplitudes will make decisions that serve their future selves well in aggregate, will find that their expectations are confirmed at the correct frequencies when measurements are repeated across many trials, and will reproduce exactly the experimental predictions that quantum mechanics has always made. The practical content of probability is unchanged. What has changed is its meaning. It is no longer a statement about an uncertain future that will resolve into one outcome. It is a statement about a certain future that will resolve into all outcomes, distributed across versions of the observer, in proportions fixed by the geometry of the wave function. The strangeness of this should not be softened. It means that every time a probability is assigned to a quantum outcome, the assignment is implicitly a statement about personal identity, about how much of what an observer currently is will inhabit each branch of their future. Probability has always been, in this framework, a measure of self-distribution across a branching reality. The concept was doing this all along. The many worlds interpretation makes it explicit. The redefinition of probability as a measure of experience distribution rather than outcome selection has consequences that extend beyond the interpretation of quantum mechanics. It reaches back and changes what physical law itself is doing when it makes probabilistic predictions, and it changes what it means for a theory to be confirmed by experimental evidence in a universe where every possible outcome of every experiment occurs in some branch. Consider what it means to test a scientific theory experimentally in a branching universe. An experimenter runs a quantum measurement, records an outcome, and checks whether the outcome is consistent with the theory's predictions. In a single outcome universe, this is straightforward. The theory predicts a probability for each outcome. The experiment produces one outcome, and the result either fits the prediction or strains it. Repeated trials build up a frequency distribution that can be compared against the theoretical probabilities with increasing precision. Confirmation accumulates as the measured frequencies converge on the predicted probabilities. In a branching universe, every trial produces all outcomes in different branches. The experimenter in each branch records one outcome because that is all any single branch contains, but across all branches, every possible sequence of outcomes is recorded by some version of the experimenter. There exist branches where 1,000 consecutive trials all produce the least probable outcome, with experimenters in those branches looking at results that appear to catastrophically contradict the theory. Those branches exist, those experimenters exist, and their data is as real as any other branch's data. What saves the theory from being simultaneously confirmed and refuted across different branches is precisely the Born rule weighting. The branches where improbable sequences of outcomes occur have vastly smaller squared amplitudes than the branches where outcome frequencies match the theoretical predictions. The weight of the wave function is overwhelmingly concentrated in branches where the observed frequencies converge on the Born rule probabilities across repeated trials. Confirmation of a theory is not a binary fact that either holds or does not. It is a property that holds with a weight proportional to the squared amplitude of the branches where the confirming evidence appears. This means that physical law in a branching universe is a statement about the structure of the wave function rather than about what happens in any single branch. A law that predicts outcome A with probability 3/4 is saying that 3/4 of the wave function's weight flows into branches where A is observed. The law is confirmed when the wave function structure matches that prediction, and it is confirmed overwhelmingly in the branches that carry the most quantum state weight, which are precisely the branches where rational observers following the Born rule would expect to find themselves. The picture that emerges is one in which physical law and probability are not separate features of reality. Physical law describes how the wave function evolves. Probability describes how that evolution distributes experience across branches, and the confirmation of physical law by experiment is the process of observers finding themselves with weight proportional to their squared amplitudes in branches where the wave function structure matches the law's predictions. Science is not the process of discovering which branch reality selected. It is the process of mapping the wave function structure from inside one of the branches it contains. The question was simple on its surface. If every quantum possibility happens, what does probability actually mean? The answer the chain has arrived at is precise, but it requires holding everything established across the descent to carry its full weight. Probability does not mean what it was assumed to mean at the start. It was assumed to be a measure of which outcome reality selects from a set of competing possibilities. That assumption is so deeply embedded in the ordinary use of the word that questioning it feels like questioning whether numbers mean anything at all. But the assumption fails in a universe governed by the Schrödinger equation, applied without exception. In that universe, reality does not select, it branches. And a concept built on selection has to be rebuilt on something else. What probability measures in a branching universe is the distribution of an observer's current quantum state across their future branches. An outcome assigned, probability 3/4, is an outcome into which 3/4 of what the observer currently is will flow after the branching event. The number is not tracking likelihood of selection, it is tracking the geometry of the wave function, specifically the squared amplitude of each branch, which measures how much of the total quantum state that branch carries forward. This makes probability a statement about identity as much as about physics. Every probability assignment made before a quantum event is implicitly a statement about how the observer's future selves are distributed across the branches that event will create. The observer who says outcome A has probability 3/4 is saying that the version of themselves who observes A carries 3 times the quantum state weight of the version who observes B. Both versions will exist. Both will remember making the prediction. But they are not equal inheritors of what the observer currently is, and that asymmetry is all that probability was ever measuring. What remains is something quieter than the original question might have suggested. The universe is not chaotic or lawless because every possibility occurs. The wave function evolves with complete determinism. The Born rule emerges as the unique rational response to that evolution, and physical law is confirmed with overwhelming weight in the branches where it should be confirmed. The structure is coherent, but it is coherent in a way that permanently changes what it means to say something is probable, what it means to expect an outcome, and what it means to be an observer moving through time in a reality that never chose between possibilities, but simply became all of them at once. Most of what has been established here lives comfortably inside physics and mathematics. The wave function evolves, branches form, squared amplitudes distribute quantum state weight, and the Born rule emerges as the unique rational response to that structure. The formalism is self-contained, and for most practical purposes it changes nothing about how quantum mechanics is used or how its predictions are extracted. An engineer calculating transistor behavior does not need to think about branching. A chemist modeling molecular bonds does not need to think about observer identity across splits. The predictions are identical regardless of interpretation, and the work proceeds undisturbed. But something does change for an observer who takes this picture seriously as a description of their own situation, not in their calculations, but in what they understand themselves to be doing when they make a decision under uncertainty, when they assign a probability to a future event, and when they face an outcome they did not want. Every decision made before a quantum branching event is a decision made on behalf of multiple future selves simultaneously. The observer cannot direct the outcome toward one branch. They cannot protect one future self at the expense of another. What they can do is choose in a way that distributes good outcomes across their future selves in proportion to the quantum state weight those selves will carry. A rational decision in a branching universe is one that serves the weighted aggregate of all future continuations, not one that gambles on a single future arriving. The decision theory grounding of the Born rule is also, quietly, a description of what it means to act well when your future is not a single thread, but a weighted distribution across everything you will become. There's also something in this picture that changes the relationship an observer has to outcomes they did not experience. In a single outcome universe, an event that did not happen is simply absent. It was possible, it did not occur, and it leaves no physical trace beyond the probability that was assigned to it beforehand. In a branching universe, an outcome that was not observed in this branch did occur in another. The version of the observer who experienced it exists, is having experiences right now in their branch, and carries a portion of the quantum state weight that the pre-branch observer was distributed across. That version is not a ghost or a hypothetical, it is a continuation of the same observer, living out a branch that this branch simply does not have access to. What that implies is not comfort exactly, and it should not be reached for as consolation too quickly. The version of you in another branch is not you in any sense that makes your current experience less significant or your current losses less real. But it does mean that the space of what you are, taken across all branches, is larger than any single experience can contain. Probability, understood fully, is the measure of how that larger space is weighted. And the question that opened this chain, what probability means if every possibility happens, turns out to have been a question about the shape of existence itself.